student, welcome to all of you in the next physics lecture. This is the video number 31 and chapter number 3, kinetic theory of gases and radiation. Myself, Rajesh Lagat, physics teacher. Now we have to see here the last topic in the chapter, that is the spectral distribution of black body radiation. In your exercise, you have to ask this question on this topic. Explain the spectral distribution of the black body radiation with the help of suitable graphical representation. So that we have to draw here the graph, the radiation power against the wavelength, which is in nanometer as shown in figure. First we have to see here the radiant energy emitted per unit area per unit time of the black body, which is depends upon on its temperature. Also, the hot bodies which can be radiate the electromagnetic radiation in a large range of the frequencies, and so that the rate of emission per unit area, which is also called as a radiant power, which is defined as a function of the wavelength lambda of the this emitted radiation. At the temperature increases, then the rate of emission which is also increases, and at the each temperature there is a mixture of the wavelength, and this radiant energy contains the mixture of different wavelengths, and at higher temperature the total energy radiated per unit time which is also increases, and the proportion of the energy emitted at the high frequencies, that is also at the shorter wavelength. The scientists, two scientists, the name of that scientist, Lumer and the Pringsheim, studied the energy distribution of the black body radiation, which is as a function of the wavelength lambda. They kept a source of radiation and at different temperatures, and measure the radiant power corresponding to the different wavelength. Then these measurements were represented, these measurements which is represented the graphically in the form of the curve which is as shown in figure. These are the curves, different curves. First, this is the second, this is the third, and this is the fourth. That means these two scientists, the Newman and the Pringsheim, he had studied the energy distribution of the black body radiation, and they kept the source of radiation at the different temperature, and they measure the radiant power which is corresponding to the which is at the different wavelengths. Then they have to find out the different curves which is as shown in figure for the different wavelengths. Then this diagram shows that in these curves which are showing the a variation of the radiant power and per unit area as the function of the wavelength. Radiant power against as the function of the wavelength at the different constant temperature. This is the different constant temperature which is as shown in figure. Then this curve indicates that as the power radiated at different wavelength, but this experimental observation indicated that the spectral distribution of the black body radiation, which is depends only on the absolute temperature and of this black body, and which does not depends upon the material of the body. This experimental observation indicates that the spectral distribution of that black body, which are depends upon only its absolute temperature and does not depends upon its material of that body. Then from this experimental curves, there are the some observations we have to write here also, that this observation very short. The first observation is that at the given temperature, the energy is not uniformly distributed. At given temperature, this energy is not uniformly distributed in the spectrum of that black body. Second one observation is that the radiant power that is the radiant energy emitted per unit time per unit surface area, which is emitted initially increases with the increasing wavelength. It should be increases with increasing the wavelength. Then it reaches at its maximum value, reaches at its maximum value, and then again goes on decreases. As shown in this figure, this curve increases, reaches at its maximum, and then again goes on decreases. The wavelength corresponding to this radiation of this maximum intensity, this is the lambda max, which is denoted at this temperature 5500 Kelvin, and which is the characteristics of the temperature of the this radiating body. Again, this lambda max, this is the not maximum wavelength. This is the maximum intensity of that corresponding radiation. Then the next observation is that as the area under this curve, area under these curves, which can be represent the total energy emitted per unit time per unit surface area by the black body at all the wavelengths. That means the area under this all this curve, which can be shows that, which can be represent the total energy which can be emitted per unit time per unit surface area of this black body at all this wavelength. Next observation from this experimental curves, we can say here the peak of these curves, which can be shifted towards the left, the peak value, that is the maximum lambda max, which can be the shift towards the left, which is has the a shorter wavelength. That is the value of the lambda max decreases with increasing temperature. The lambda max decreases with increasing the temperature, and this is very important observation from this experimental curve. And also we can say the last observation is that at the higher temperature, the radiant power is nothing but what? That is the total energy emitted per unit area per unit time. That is the total energy emitted per unit time per unit area. This is nothing but the radiant power, and which is the corresponding to the all the wavelength increases. This shows that wavelength increases, then this is nothing but the at temperature the radiant power, which is corresponding to the all the wavelength, it should be the increases. And this is nothing but the observation from this experimental curves, that is the radiation powers against the wavelength, and which can be the given by these two scientists, the Buber and the Pringsheim, which can be studied this energy distribution of the black body and gives this graphical representation. And from this experimental curve they give some observations, and this is very important. And this theoretical explanation of these above observations, which cannot be given by the existing theories, the scientists, the name of that scientist Wines, which gives the expression for the spectral distribution, and from the laws of thermodynamics, which is the next we have to see the Wines this distributive displacement law, that is the lambda max is inversely proportional to the T, that is the absolute temperature. So this is the about the explanation of spectral distribution of the black body radiation. Okay, now I stop there.